Thanks, Nino, and the other organizers for inviting me to speak here. Here's a plan for my talk. I want to address the following questions. Is Bohmian mechanics local or non-local? Are collapse theories such as GRW local or non-local? Is the Orthodox or Copenhagen interpretation local or non-local? Is the Manyworlds theory local or non-local? Can the Manyworlds theory be made relativistic? Can the Orthodox or Copenhagen interpretation be made relativistic? Can Bohmian mechanics be made relativistic? Can collapse theories be made relativistic? And I intend to answer all of these questions in my talk. Perhaps I should first give a statement of what I mean by locality, or the negation of which then is non-locality. So consider two space-time regions. So here is space-time, space and time, region A, region B, these ellipses. Then
you can start from the questions, because Roger is here. I would like to ask Roger to follow the talk.
Okay. So I will address 8 questions in my talk for 4 different types of interpretations of quantum mechanics, for each of which, whether it's local or non-local, and for each of which, whether it can be made relativistic. Local, so let me give a definition of locality. We have 2 space-time regions. Now the future of region A, so region A is this thing here, the future of region A, that would be all points that lie in the future of any space-time point in A. So that is this region here, A as well as everything up here. So this is kind of the light cone, the future light cone of A. This is the past light cone of A. What's outside those light cones, that is from here onwards, that is what is space-like separated from A. So the region B lies entirely in that region, so A and B are space-like separated. And I would say if the space-time regions A and B are space-like separated, then events in A cannot influence events in B. So that's what I take to be the meaning of locality, at least in single world theories. In many world theories, everything comes a little more complicated due to the existence of several worlds. Okay, first chapter is Bohmian mechanics, local or non-local.
Just event. Small definition?
My definition, events. Okay.
Definition of the event.
I didn't understand the question.
Well, what is the definition of the word event?
I guess that depends on the theory. The theory tells us what events are. Okay, events in A, events in B. I guess it will not be a practical problem given a theory such as Bohmian mechanics to decide what are events in A. Okay, if you have doubts about this, ask me later. Okay. Good. So here's the definition of Bohmian mechanics again. So the picture has these Bohmian trajectories for the double slit experiment, a number of alternative trajectories that the particle could take in a double slit setup. Here's the equation of motion. Okay, so if you're not familiar with this equation, don't worry about the details. Some equation of motion, some which involves psi, depends on psi. There's some, the evolution of psi is given by the usual Schrödinger equation. And another fact that at any time t, the configuration is psi squared distributed. So if we assume that at one time, then it follows at any other time. Good. Now, Bell's theorem applies to this theory. And this is some additional information about how it implies. So this refers to the formulation of Bell's theorem in terms of the conditional probability of particular outcomes A, B, conditional on settings of the parameters, as well as some lambda, where the lambda describes all of the facts or variables or information that is fixed already in the common past of the two regions A and B. So I can say explicitly for this theory what the lambda will be. It will be the psi. So for a Bell experiment, this would often be the singlet state for the EPR pair, and x the configuration of the particles, so the two initial positions of the particles. So Bell's theorem then simply shows that Bohmian mechanics is non-local. At the same time, one can prove that there is no signaling. That is, I should perhaps say more carefully, when the Schrödinger equation that you use is relativistic, if it's the Dirac equation, so wave functions can't propagate faster than light, then you can show that actually you can't send any signals from A to B. Well, the fact that Bohmian mechanics is non-local can be seen much more directly than by Bell's proof. It can be seen directly from the definition of the theory. The velocity of particle 2 by the very equation, that is the law of motion for particle 2, depends on the position of particle 1. Let me go back one slide. Here the velocity of particle I depends on the positions of all particles, no matter how distant and no matter whether there is an interaction term in the Hamiltonian. So this is where the superluminal influence occurs, which means that the theory is non-local. And, well, in this case, I guess there is no question about what counts as an event. Good.
I think the event is not proper here. What event?
Events, we're talking about events such as the particle passing through a particular space-time point. That's an event, right? And we can ask whether these events are influenced by other events that occur in A. This influence depends on entanglement. In the absence of entanglement, the velocity of particle 2 is actually independent of the position of particle 1. Let me go back one slide again. Again, this can be read off from the equation of motion. Actually, if psi factorizes for the two particles, then in the equation for particle 2, the factor for particle 1 just cancels out of the equation. The behavior of particle 2 doesn't depend on that of particle 1, doesn't depend on the position of particle 1. So that shows that entanglement is actually necessary in order to get non-local effects to occur, non-local influences to occur in Bohmian mechanics. This also means that the fact that Bohmian mechanics is local for relativistic Hamiltonians, such as in the Dirac equation for disentangled wave function, shows that it is necessary for proving non-locality to consider at least two particles and an entangled wave function. Good. So for Bohmian mechanics, the discussion was very easy. Let me move on to the next chapter, collapse theories. I will just use the GRW theory as a paradigm example of a collapse theory. Here is a summary of the definition again. So the wave function evolves for certain time intervals unitarily according to the usual Schrödinger equation. The duration of this time interval is random, with a mean duration of 10 to the 8 years divided by the number of particles. So for one particle, the GRW collapses occur every 100 million years. When you have 10 to the 23 particles, then a collapse occurs like every 10 to the minus 7 seconds. So at this random time of collapse, the psi changes discontinuously. The psi gets replaced by a different wave function according to a certain precise rule. You randomly select one of the particle labels, or, well, I should say, in this theory, there actually are not any particles. There's just wave function and maybe some other stuff. So I then refers to one of the variables in the wave function. You select one of them randomly. You select a location in physical space randomly with a distribution that is the following. You start with the psi-square distribution, which is a density function on configuration space. You form the marginal for the ith variable, kind of the psi-square distribution for the ith particle. This star means convolution with a Gaussian. Okay, that's a technical detail, don't worry about that. And then that's how that means you fatten up this distribution with a certain width, sigma, 10 to the minus 7 meters, the localization length, and you replace the wave function by the wave function times a Gaussian. So here's a picture. That is the wave function. Well, say what's shown here in the graph is the real part of the wave function, let's say, on configuration space of two particles in one dimension. Now, we choose this particle for the collapse process. And in this variable, we localize the wave function to this length, 10 to the minus 7 meters. Here you can see the Gaussian. So multiplication by a Gaussian sets the wave function basically equal to 0 outside that region, and that's what the collapse looks like. And then you repeat. You wait for again, or nature waits again for a random time, etc. In addition to this evolution of the wave function in the GRW theories that I want to talk about, you also have a primitive ontology, that is something that represents matter in space and time. I will consider two versions of that, GRWM with a matter density function or matter density ontology, GRWF. So in this theory, this theory claims that matter is continuously distributed in space with the density function given by m, depends on time and on the space point, of course. So bold-face symbols means 3 vectors, and this function. So this is one of the laws of the theory, and it says, oh, you take the psi-square distribution, then you integrate out all the variables except one. So this integral with the Dirac delta function here essentially means that you form the 3-dimensional marginal of your 3n-dimensional density function, and then here you average over which index I, which particle you took. And you could use different weights here, and one kind of particularly natural choice is to use the masses of the particles as the weights. Good. So you get a mass distribution in space that changes over time and in fact changes in a stochastic way because it's a function of psi, and psi evolves in a stochastic way. Psi evolves according to the GRW process. So in this other version, GRWF, you still use a psi that evolves according to the GRW process, but now you make a different claim about what is the primitive ontology, what is the matter in, in space and time. You claim that matter consists of flashes. A flash is a material point in space-time. So a particle has a world line, a flash has just a world point. So there's just a discrete set, maybe a finite set of points in space-time where the matter is. Here's a picture of that. So that's a 2-dimensional space, 1-dimensional time. So here in this picture, you see about 2,000 red dots. Each dot represents a flash. So that picture conveys how, kind of on a macroscopic scale, you could have shapes that consist of many, many little flashes. The law for where to put the flashes is the following. For every collapse of the wave function, you put one flash at the time of the collapse at the location that's the center of the collapse. So for a system of 10 to the 23 particles, you will have about 10 to the 7 flashes per second. So that gives you an idea of how macroscopic objects, tables, etc., can actually consist of flashes. You can have a pattern of flashes that is recognizably a table, has the shape of a table. Good. So that's the definition of the theories. Now, are they local or non-local? The answer is they're non-local. Here are several proofs of that. Number one, both GRWM and GRWF predict with tiny deviations the same probabilities of outcomes of EPR Bell experiments, and in fact of more or less any quantum experiment, as the quantum formalism. Thus, Bell's inequality is violated, and here for applying Bell's theorem, you would have to consider lambda equal to psi. So all the, where psi, well, in this case, would again be the singlet state for the two particles. Here, there is no, since there are no further variables besides the wave function that are not functions of the wave function itself, the only variable that is that provides common information to both particles, the only variable that is in the common past of both experiments at A and B is just the wave function. Then you apply the reasoning of Bell's theorem, you obtain that these theories are non-local. Again, there's a no signaling theorem in both theories. And again, you can see much more directly that these theories are non-local. Collapsing the wave function in one variable, x1, can instantaneously change the psi-square distribution for x2, that is the marginal of the psi-square distribution for x2, and therefore change the m function in GRWM, because that is defined in terms of such a marginal, in region B. Therefore, a collapse in region A will have an instantaneous change of the m function in region B. That shows it's a non-local theory. Likewise, for GRWF, a flash in region A, flash goes together with a collapse. So a flash in region A associated with a collapse centered at some point in region A will change the probability distribution of the next flash in region B. Now consider a situation where you have 10 to the 7 flashes per second in each region. Okay, so from the empirical distribution of these flashes in region B, you get some information about what this probability distribution was. Here's a third reasoning that I think is instructive, that shows that these theories are non-local. They are actually already non-local in a simpler setting than Bell's. So Bell considers two entangled particles, and we saw in Bohmian mechanics that this is necessary in order to prove non-locality, because if you have fewer than two particles, or if you have a disentangled wave function, then Bohmian mechanics will be local. Here the situation is different. There is a certain situation of just one particle in which GRW theories are already non-local. This example is known as Einstein's boxes. It was described by Einstein, I guess, around 1927 or something. A nice paper describing it is by Travis Norrison, appeared in the American Journal of Physics 2005. So here's the example. The wave function of a single particle is half in a box in Paris, half in a box in Tokyo. So it looks like this. We have these two bumps that are pretty far away from each other. Now apply detectors to both boxes. So the boxes, say there's a box here and a box there. Okay, that's the idea. That's why it's called boxes. Apply a detector here, apply a detector there. Then the outcome will be one and only one detector clicks, say 50% probability here, 50% there. Now, so far that's not surprising in any way. Now comes the argument. If it is assumed that there was no fact about where the particle actually is, which of the detectors will click, before the detectors were applied, then this effect is non-local. So in this experiment, there doesn't have to be any non-locality. Bohmian mechanics is an example of how you could explain this outcome in a completely local way. Namely, you simply assume that all the time the particle was in one of the two boxes, and the detectors simply discover which box the particle was in. Okay, nothing non-local. But if you assume that there was no particle, and if you assume that there was no fact of the matter about which detector will click before you apply the detectors. If you believe that the outcome of this experiment was not predetermined by any further variables in addition to the wave function, then this effect is non-local. What is non-local about it is that the two outcomes have to be anti-correlated. If one says yes, then the other has to say no. And this you couldn't do without non-locality. If you had to do it in a local way and there was no fact predetermining it, then if one said yes, then the other would still have to make a random decision. Good. So Einstein intended this as an argument against the Copenhagen camp. And here I use this argument to prove that any collapse theory is non-local. That's because...
Kind of non-locality, this sort of simple kind of...
Right. You had basically the same kind of reasoning. Here, because collapse theories do make this assumption that there is no fact about where the particle actually is before you apply the detectors, because only when you apply the detectors, because the detectors consist of many particles, like 10 to the 23, that you force the wave function of the whole system to collapse in such a way that you get a fact about what the outcomes will be. And that is why this shows non-locality of collapse theories. In both GRWF and GRWM, you can get the non-locality already. In fact, with the similar reasoning, a bit simpler without detectors, because you can basically make an argument that the spontaneous GRW collapses can already play the same role as the detectors. So I will show now that the GRW theories already in the case of a single particle, in a single particle universe, are non-local. Here's how. Consider again such a wave function as in the Einstein boxes example, and now instead of Paris and Tokyo, let's say they're really far apart, like 500 million light years. Why did I choose 500 million light years? Because in the GRW theory, for a single particle, a collapse will occur typically every 100 million light years. So I want to, every 100 million years. So I want to have a distance that gives me a high probability that there will be a spontaneous collapse. Okay, so what will happen is that on both sides you will have these spontaneous collapses, and actually the first collapse will set the wave function to essentially 0 on one side and kind of double it on the other side, and then once that has happened, then all the further collapses have probability very near 0 to be on the disfavored side, and all the collapses will just be on the one side. So what this means is that the spontaneous collapses essentially give the same kind of outcome as your detectors would give you, a non-local influence. Good. Orthodox or Copenhagen interpretation, local or non-local? I claim it's non-local. First, it's hard to define what the Orthodox or Copenhagen interpretation actually says, but nevertheless it seems clear enough that it asserts that a quantum particle does not have a position before we do a quantum position measurement. Thus, Einstein's boxes argument applies and shows that orthodox quantum mechanics is non-local. It's simply a valid argument. It actually proves that orthodox quantum mechanics is non-local. Likewise, it seems clear enough that orthodox quantum mechanics denies any hidden variables. Hidden variables is, of course, a kind of misleading name for any further variables beyond the wave function psi. So Bell's theorem applies again with lambda equal to psi. This is sometimes not well understood because people seem to think that lambda is something like a hidden variable, and that Bell's theorem somehow, if the statement or the formulas involving conditional probabilities involve some lambda, then that, it is often said, means that we're somehow assuming hidden variables. Well, if there are no hidden variables, that simply means that lambda is the same thing as psi. Okay, that's all there is in the common past of the two particles. Good. You apply Bell's reasoning with lambda just equal to psi, you get out that locality is violated. Still, orthodox physicists usually reject non-locality and claim that orthodox quantum mechanics was local. This is just incorrect. Now, the question arises, why do people say that? I would say physics is hard, psychology is even harder. It's kind of very difficult to actually pin down why people are saying that. I have the sense there's some kind of incoherence in their reasoning. Well, I can offer some speculations. Number one, historically, Einstein's boxes argument first came as an objection to orthodox quantum mechanics at a time when locality was regarded as a fact and thus historically had to be rejected by the orthodox camp with whatever excuse or whatever reasoning. Also psychologically, it seems to me that orthodox physicists often do think in terms of hidden variables in spite of their announcements that they reject hidden variables. When they try to imagine certain situations, they actually do think of it in terms of hidden variables. This, I think, has something to do with their inclination to positivism, where by positivism I mean the idea that only operational or testable statements are meaningful or scientific. So I think their inclination to positivism seems to keep them from appreciating the difference between assuming that there's a fact about what the outcome of the detection will be before you apply the detectors, and assuming that there's no such fact before you actually apply the detectors. So the difference between the two options, I think, is usually not clear to an orthodox physicist. And that has something to do, I think, with the fact that the question is not an operational question, not a testable question. The question whether already before doing the detection, there's a fact about what the outcome of the detection will be. I think the moral of all this is that you cannot understand non-locality if you do not think about what happens out there in reality. If you, as many orthodox physicists do, refuse to think about reality, and if you insist on a positivistic attitude, then you just don't understand, you can't understand what non-locality even says.
Yeah, and then you identify it with signaling, superluminal signaling.
And you can't understand what those people talking about non-locality are talking about. Right. What's all the fuss about? Good. So that was the chapter on orthodox. Now, Manyworlds. Is the Manyworlds theory local or non-local? Okay, I should first begin again with the definition of the Manyworlds theory. Okay, so here, I guess it was first really advocated by Everett, 1957, in the following form. There exists only the wave function psi of the universe and nothing else. Psi evolves according to the usual Schrödinger equation, and the superpositions, the different contributions corresponding to macroscopically different situations, then represent parallel, equally real worlds. To me, this doesn't actually make sense as a fundamental physical theory, because I think such a theory must have a primitive ontology, some variables representing matter in space-time, such as flashes or particle whirl lines or something like that. But this problem that I have with this formulation can be solved with a different formulation, which in fact had historically already been given before by Schrödinger in 1926. according to this proposal, matter is continuously distributed in space with a density that's given by exactly the same formula as we had before in GRWM. Same formula, but now a different wave function. Here it is assumed that psi evolves according to the usual Schrödinger equation instead of the collapse process. So that means in particular that when you have a wave function that is a superposition of two wave packets located in two regions of configuration space that correspond to macroscopically different situations, like different measurement outcomes, pointer pointing here, pointer pointing there. In such a situation, your M function will look as follows. You will, because these two contributions to the psi function have no overlap in configuration space, they have disjoint supports, you will not see any cross or interference terms between these two contributions, and what will happen is that the M function is simply the sum of two contributions to the M functions, each coming from one of the two contributions to the psi function. So what happens is that the whole M function is a sum or some linear combination of two M functions, each of which make good sense as the matter density of an ordinary situation, of an ordinary state of affairs. So it's a bit like watching TV and you can't tune it correctly, so you always see two different channels at the same time. Maybe if you're smart enough, you can actually watch two movies at the same time. In this way, figure out which parts belong to which movie. That's kind of similar to what happens in this theory. Okay, I will call this theory SM, where S, so that's a bit analogous to GRWM. S is for Schrödinger equation, the evolution for psi, and M is for the primitive ontology. And then in this notation, Everett's proposal would be S0. Where
Only if you have super technology. Because usually you will be split in, there will be one movie for each one. So your analogy.
Yeah, okay, no, you misunderstood what I was saying. So the reality in SM is a bit like what you see on this bad TV, okay?
So the God's view.
God's view, exactly. Yes.
So my very trivial remark was that the mass density said that if you speak of the two pointers, actually the mass density corresponding to the two positions is 1/2 of the density of the mass density of the original pointer when it was pointing at 0.
That is exactly right. So the mass density here has two contributions, and then there's a copy of every person and every table in each of the two contributions, but the two copies of me in these two contributions may be in different configurations, and they don't interact with each other because just the way the Schrödinger equation works, you see interaction just within each wave packet. You don't have interaction between the two wave packets because the two wave packets would correspond to, in other interpretations, Bohmian or Orthodox, to alternative possibilities. So there are two copies of myself which don't notice each other, which walk through each other, and but I can interact with a certain copy of Shelley, while the other copy of myself can interact with another copy of Shelley. So that's why this theory is really a many-worlds theory. Good. Now I claim that this theory is non-local. Here is why. By the way, this whole theory, SM, and also its locality or non-locality is discussed in detail in this paper. You might at first think, and I did at first think, that SM was local because of the following fact. The matter density in region B does not depend on external fields applied in region A or on the quantum state in region A. It is a function of the reduced density matrix that you obtain for region B when you trace out all degrees of freedom in region A, where psi may include any apparatus or the brain of Alice who has already kind of some decisions about which parameters to choose or something like that, or what message to signal. Okay. So it is a fact that the matter density in B does not depend in any way on what Alice can do in region A or on any events in A. And yet I claim that Sm is non-local. Here's why. Consider Einstein's boxes scenario at a time t after applying detectors on both sides. The possible outcomes of the experiment are 0, 1. That means this detector says 0, this detector says 1, or 1, 0. Now the wave function at that time, the wave function of the universe, now has two contributions corresponding to these two possible outcomes, and corresponding in the Manyworlds view to two possible worlds, one in which the outcome was 0, 1, 1, 1, 0. Correspondingly, the M function has now these two contributions, one in which this pointer is 0, this pointer is 1, and one in which it's opposite. Okay. That means the world in which Alice's result is 1 is the same world as the one in which Bob's result is 0. And this fact is created in a non-local way. This is something that would not be possible in a local many-worlds theory. In a classical many-worlds theory, for example. It is a non-local fact because it connects the outcome in Tokyo with the outcome in Paris. The M function alone, while revealing that there are two worlds in A and two worlds in B, does not encode the information conveying which world in A is the same as which world in B. That is, the pairing of worlds cannot be read off from the M function at that time, even though it is an objective fact in that theory at that time, because it can be defined by means of the wave function at that time. Thus, the fact that Alice cannot influence the M function in B does not mean locality. So that's why the previous reasoning, which suggested locality, is actually wrong. One should suspect already that Sm is non-local when noticing that it involves a non-local object psi and cannot, at least not in any obvious way, be formulated without mentioning such an object. So the fact that we have this non-local wave function should already suggest to us that this is a non-local theory. Moreover, even though Alice cannot influence the primitive ontology in B, she can influence other physical facts pertaining to B. So now I'm coming back to Lev's definition of non-locality. If I have an agent, Alice here, can she do something that will change the situation on the other side? And I claim in Sm she can. Here is my example, what she can do. Consider a Bell experiment. Now this example is a bit more complicated than the previous one. A Bell experiment with two electrons starting in the singlet state. Alice chooses for her magnet either the x or the z direction, while Bob always chooses the z direction. Okay, so this setup would not be good for proving non-locality with Bell's argument. But nevertheless, let's consider this setup. Okay, so Alice has a choice between two different directions. Now suppose that at time t in a certain Lorentz frame, Alice's detector has already clicked, but Bob's has not, although Bob's particle has already passed Bob's magnet. So on Bob's side, the electron has passed, or the electron wave function has passed through the magnet, so split up, but no detection event yet. Okay, that's a bit complicated choice, but now we can see what happens. Now, here I'm talking about the M function on Bob's side. So remember that on Bob's side, the wave function has split up into these two bumps. Correspondingly, the M function will have two bumps. And since Alice's detector has already clicked, we have two worlds corresponding to the two possible outcomes on Alice's side. Now we can take the M function of the universe and split it up into these two into these two worlds. And now the point is, what does the splitting look like? We know already that nothing that Alice can do will influence the M function on Bob's side. But now we're talking about something else, about how the M function splits up into two worlds on Bob's side. Okay, so here are the two locations. For Bob in the z direction, where the two bumps of the M function can be. Okay, so the total M function has one blob here, one blob there. Now we split the M function up into a sum of two contributions. Okay, in one case, if Alice chooses z, then the splitting of the two worlds actually looks like this. In one world, the M function is just down here. In the other world, the M function is just up here. Now this is in Bob's lab, okay? The M function in Bob's lab. However, if Alice chooses x, then the splitting of the total wave function into two worlds is different. The splitting of the M function into two worlds is different. And in each of the two worlds, actually, the M function in Bob's lab has one blob here and one blob there. That is, while the total M function at spacetime points in region B is unaffected by Alice's choice, each contribution M sub L corresponding to the different worlds is affected. Okay, so that's my example, or our example, for how Alice can influence the state of affairs in region B. Okay, I talked so far about SM, but I think the same kind of reasoning applies to any version of Manyworlds. Okay, so I would say that Everett's version is just as non-local for the same reason. Good. So I've talked about 4 different views of quantum mechanics, about whether they're local or non-local. Now, about whether they can be made relativistic. Now, I proceed in a different order. Let me start with Manyworlds. That is, let me start with SM. Can SM be made relativistic? The answer is very easily. That is, very easily, at least, if we neglect certain problems, certain sort of technical problems. Let me neglect the fact that nobody can actually write down a Hamiltonian that is mathematically well-defined, appropriately Lorentz covariant, and involves interaction. This is related to ultraviolet divergence in quantum field theory, renormalization, and other such things. Now, to the extent that anybody can write down any Lorentz invariant Schrödinger equation involving interaction, my claim is, yeah, well, you can write down a relativistic version of SM. Okay. And here's how you do that. Consider a relativistic Hamiltonian. Let's pretend we have that. Let's use the Heisenberg picture with a fixed state vector psi. Let T mu nu be the stress energy tensor operator for the spacetime point T, x. And then define the M function, which now becomes a tensor. In this way, you take this operator-valued field, or operator-valued function on spacetime, you sandwich it between psi, you get some number. Okay, it depends on T and X, so that is your mass density. We're used from general relativity to the idea that that mass density can become a tensor. Okay, so now it is a tensor. Good. And matter is continuously distributed in space-time with density given by this tensor. So this theory is relativistically invariant if the underlying equations for H and T mu nu are. Good. So this is an attractive feature of SM, that you can easily make it relativistic. How about the Orthodox or Copenhagen interpretation? Again, it's kind of not so easy to answer because it's hard to define what Orthodox quantum mechanics actually says. So it's much easier for the other 3 views of quantum mechanics to give a clear answer and to say what a relativistic, to give equations for what a relativistic version could be. Well, at this point we could say, it says something like, macroscopic quantities always have definite values, microscopic ones do not. The interaction between the two is governed by the Born rule and the collapse rule. So that is how the macroscopic variables are affected by the microscopic ones and vice versa. Then the mathematical laws could be stated as just the rules for making predictions And let us pretend again we have a relativistic Hamiltonian H with interaction, then a relativistic formulation of orthodox quantum mechanics would seem to require just the formula for the joint distribution of the outcomes of quantum measurements of the local observables A1 through AN at space-time points T1 x1 through Tn xn, and this probability distribution can easily be worked out. It's given by this formula where we have numbered the points according to increasing times, and UK are the unitary operators evolving from one time to the other. PK are the projections to the appropriate eigenspaces. So this is a completely standard formula, and this formula can be shown to be invariant to be independent of the Lorentz frame using that local observables at space-like separation commute. Good. So if orthodox quantum mechanics were satisfactory, then I guess it would be easy to make it relativistic. Can Bohmian mechanics be made relativistic? This is actually the title of a recent paper by Detlef Shaley-Nino, Travis Norrison, and Ward Struve. There are two more references here I mentioned. This paper is called Hypersurface Bohm-Dirac Models. And here in this one I have some further remarks on this question. The basic situation is the following. If a preferred foliation means slicing of space-time into space-like hypersurfaces, is permitted. So here's a picture of this kind of slicing. So this means T, this means X, so this is space-time here, and now here we have these surfaces. So through every space-time point there is exactly one surface. All these surfaces are space-like. Good, so this is an example of such a foliation. I call this a time foliation and write script F for that. So if we allow ourselves to use such a foliation, then there's a simple, convincing analog of Bohmian mechanics. Let me write that, Bm sub F. Without a time foliation, no version of Bohmian mechanics is known that would make predictions anywhere near quantum mechanics. And I have no hope that such a version could be found in the future. Now, some people would say that's not relativistic if you use a preferred foliation. Once you think about what it means for a theory to be relativistic, it turns out that there are kind of many candidate properties. It's easy to come up with half a dozen or a full dozen different properties that a theory might or might not have that could be understood as expressions of the theory being relativistic. Now, I guess there's no convincing case that any of these properties just hits the nail on the head and expresses that is what relativistic means. It seems like it becomes a discussion about words, about how to use the word relativistic. So it's not very clear whether this particular theory, Bm sub F, the hypersurface Bohm-Dirac model, should be regarded as relativistic or not. But be that as it may, I think it's a theory worth considering. It's a possibility worth considering that our universe is of that kind and has a time foliation. That leads to the question, okay, which foliation is it? Here's a particular simple choice. Here I borrowed this drawing from Roger Penrose, who has so many very nice drawings. This is the universe, okay? So this is Friedman, Lemaitre, Robertson, Walker universe, a cosmological solution of Einstein's equation. So here, this is where time goes. And of course, what is drawn here is just one space dimension. Here is the Big Bang. Okay, so this particular Lorentzian manifold has an initial singularity. Okay, so let's assume that our universe looks like that. It has an initial singularity. Then let the foliation be given by the level sets of the following function t, a function on space-time with real values. for every space-time point x, t is the time-like distance of the point x from the initial singularity. So for here now, a particular space-time point, this t value is about 13.7 billion years. So these surfaces, and actually Sir Roger has nicely already drawn one of these surfaces in his picture. These surfaces are the surfaces that have constant distance from the, that are sort of parallel translations of the initial singularity. This is perhaps the simplest choice of a preferred foliation that you could have in such a universe. Alternatively, the time foliation might be defined in terms of the quantum state vector psi. So f would be a function of psi, and this is discussed in some detail in this recent paper. Or the foliation might be determined by an evolution law, possibly involving psi, from an initial time leaf. Good. The mathematics of Bohmian mechanics, given such a foliation, actually works for any given foliation. Here are some key facts about this theory. It's known in the case of n non-interacting Dirac particles, and expected to be true also, say, one day in full QED with photon trajectories. First, that this equivariance property, suppose that the initial configuration is psi squared distributed, then on every leaf of the time foliation, again, the configuration is psi squared distributed. This does not mean that the configuration is psi squared distributed on every surface, just on every time leaf, on every surface that belongs to this preferred foliation. On other surfaces, actually, the intersection points of the word lines through the surface could be differently distributed. Still, it is true that detected configurations are psi squared distributed on every space-like hypersurface. That means the following: if you place detectors along the surface of your choice, then the presence of detectors will have some influence on what the trajectories actually are, because if some detectors are applied earlier with respect to the time foliation than others, they will have an effect of collapsing the wave function. Good, so in the presence of detectors, your intersection points are actually psi squared distributed on every space-like hypersurface. As a consequence, this time foliation is invisible in the sense that experimental results reveal no information about which foliation the time foliation is. So inhabitants of a universe governed by this theory have no knowledge about what the correct foliation is. There is one foliation in the universe that's the right one, and inhabitants have no information about what it is. So that's the status in Bohmian mechanics. How about collapse theories? Everybody's first idea is that if collapse is instantaneous as opposed to propagating at speed c, then it must violate relativity. This problem can easily be avoided by taking up the idea that you have a wave function psi sub sigma for every space-like hypersurface sigma. So for every space-like hypersurface, you have a separate Hilbert space. That could be the one-particle Hilbert space and the tensor power and the one-particle Hilbert space. This would be what it is, for example, for the Dirac equation. Relativistic collapse processes, that is stochastic evolution laws for psi, have been proposed in different ways. None of these proposals is a complete solution of the problem. So proposals of 1990 involve relativistic continuous collapse processes. However, suffer from divergences. A recent modification due to Bedingham removes the divergences, but has some element in it that actually breaks the Lorentz invariance. Another process that I developed is a relativistic version of the discrete GRW process for n non-interacting spin 1/2 particles in an external field. Now, all of these processes, well, to the extent that they work, have kind of the following structure in common. given an initial wave function on some initial surface and possibly further initial data, the law for the wave function specifies the joint distribution of the wave functions at all surfaces in the future of the initial surface. In situations in which the unitary Schrödinger evolution would lead to a superposition of macroscopically different contributions, such as Schrödinger's cat, the law for psi yields that the actual wave function is just approximately just one of these contributions with the appropriate probability. And for any two hypersurfaces, after a local measurement at a space-time point y, the two wave functions on these two different surfaces select the same outcome, the same alpha of that measurement. Good. Now, with this process for the wave function psi, still a problem remains. How do we get facts? In fact, this is a problem that has been discussed many times over the decades. Let me describe the problem as follows. Consider a space like hypersurface. Here is part A. Here is part B. Here is part B prime. Okay, two different hypersurfaces that have half of them in common. Okay, now consider tracing out the part B and just consider the reduced density matrix for part A. Okay, that will depend on the choice of B. That's because in a collapse theory, the wave function on AB may be different, quite different from the wave function on AB prime, and in fact in such a way that their reduced density matrices may still be quite different. For example, in an EPR experiment where say Bob's measurement occurs at a space-time point or space-time region between this A and B, then you will have the following. Before this measurement on Alice's side, you will have a reduced density matrix that is 1/2 times the identity. After the collapse, you will have a pure state on Alice's side. So a different reduced density matrix. So that leads to the question, in one case you have a pure state, in the other case it will be mixed. So the question here is, what are the local facts in region A? What are the local facts in this room, given just the wave function? If the facts depend on how you extend the hypersurface outside of this room, that seems unsatisfactory. That seems inappropriate. Local facts here should not depend on how we extend our hypersurface in the Andromeda galaxy. The solution, or a solution to this problem, is provided by primitive ontology, variables representing matter in spacetime, such as the matter density ontology or the flash ontology. So here, let me quote from this paper. We should demand that certain local facts, such as whether a cat is dead or alive, do not depend on the choice of sigma. Fortunately, the macroscopic local situation is practically unambiguous. But the notion of macroscopic is imprecise. The variable that defines local facts need not define a spin state for every particle, but it should define the distribution of matter in space-time and ensure that macroscopic configurations are unambiguous. So that is an explanation of why one would arrive at the requirement to have a primitive ontology and why these primitive ontologies do the job. So with a flash ontology, we've seen this picture before. So the relativistic the version of GRWF that I'm here referring to includes a relativistic version of the GRW process, with a collapse occurring at a random proper time t after the previous collapse for the same particle. A flash occurs at the center of every wave function collapse. So again, you obtain in a relativistic way a pattern of flashes such as this. So that's how you obtain a theory. You can obtain macroscopic objects that you can recognize in this pattern of flashes. In fact, in such an EPR situation, there is no fact about who influenced whom. The theory is non-local. you get the Bell correlations. Bell's inequality is violated. So there must be an influence, but there is no fact of the matter about the direction of the influence. So that means the following. In a Bell experiment, say on Alice's side, you could detect the particle either here or there. Say this is the up channel, this is the down channel. On Bob's side, Bob could detect the particle either in the up or in the down position. Now, let's say, for simplicity, let's not use detectors, let's use 100 million years instead, because then the spontaneous collapses will do the detection job, will do the decision about where the particle and the wave function will be. So there's a flash that occurs on the A side. It occurs with 50% probability in this region and with 50% probability in that region. Okay, so we make a random decision. Somewhere it does occur. On Bob's side, a flash occurs in a random point, one of these two. Okay, now the joint distribution of these flashes is correlated in a non-local way, but nevertheless, agents have no way of influencing that. Okay, other than setting their magnets, which determines the joint distribution. So what happens here is that there are two random events in nature which are correlated in such a way, in a non-local way, but there is no fact of the matter about which way the influence went. So that is like you have two random variables which are correlated, then there is no fact of the matter as to which random variable influenced the other one. So for example, you could imagine that this flash occurred first, and once you imagine that, that changes very much the conditional probability distribution of the other flash. So the other flash would have to react to this in a non-local way. But you could just as well imagine that the flash on the B side occurs first, and then the flash on the A side has to react to that. But none of these two pictures actually represents what is really going on, because for what is really going on, there doesn't have to be any fact of the matter as to which was first and which one was influenced. You could just have, according to the theory, you just have the two flashes which occur with a joint distribution that is non-local. Now for GRWM, also a relativistic version of GRWM can be set up. That was in this recent paper. So this is again the law for the M function. In the non-relativistic case, here's the relativistic version. Essentially the essential difference is this. Instead of simultaneous wave function, use the wave function on the past light cone. Okay? PLC is for the past light cone. So in order to compute the wave function at any space-time point x, consider the past light cone of x, consider the wave function and the appropriate mass density operator on that surface. You form the appropriate inner product on that surface. You get this quantity. Okay, here are some details about what that would actually look like for the Dirac equation. Never mind. So here is what it looks like in the Einstein's boxes example. When you start out with two wave packets, Paris and Tokyo, and a detector in the ready state, or two detectors. Say, initially, okay, so here's the space-time diagram of the M function. So here the M function is 1/2, here it is 1/2, and here it is 1. Okay, so at this point, the space-time point, for example, we use the past light cone in order to determine the M function. Now this symbol here represents a detector. We apply a detector here. The outcome of the detection is 0. Okay, which corresponds to the fact that ultimately we have 0 M function here and 1 M function over there. But at this space-time point, the M function at this space-time point, according to the law of relativistic GRWM, is determined by the wave function on that past light cone, which is still uncollapsed because the duration of this experiment is less than 100 million years, and the detector, which increases the rate of collapse, is applied only at this time tau. Good. So that means on this past light cone, the wave function is still uncollapsed, and that is why the m function is still 1/2 over here. So that is what the theory says. Okay, 1/2 here, 1/2 here, 1/2 here, 0 here. So at this time, actually, you notice that the m function is not conserved. It's 0 here, 1/2 here. Now, when seeing this, you might be worried that if I apply a detector over here, that I might only have probability 1/2 of getting the result 1, which would be bad because I need to have probability 1 to have this result. Now here is what actually happens if you apply a second detector. Then the equations of the theory simply make sure, because of the collapse process for the wave function, that the outcomes of the two detection experiments are perfectly anti-correlated. If you get 0 over here, you get 1 over there, and as soon as you have a detector here, you collapse the you have a collapse over here, you change the m function also over here, because at this point, in the past light cone of this point here, even though the past light cone is still before that detection event, it's past that detection event, so the wave function is already collapsed, so you have mass density 1 over here. Good. Good. Yeah. So here's the last things I want to say. For any of the known relativistic collapse processes for psi, suppose that a local measurement is made at a space-time point y, then the m function in the future light cone of y and the psi function on any hypersurface after y agree about the outcome. The empirical predictions of this theory agree approximately with the quantum formalism to the same extent as normal GRW theory, non-relativistic GRW theory agrees with quantum formalism, non-relativistic quantum formalism, makes the same predictions approximately. In the non-relativistic limit, this theory just becomes non-relativistic GRWM. There's a no signaling theorem with kind of some subtle exceptions at very small distances. Okay. There's a property called microscopic parameter independence. Let me not talk about this. And of course, it's a non-local theory. Thank you very much for your attention.